Hello, this is Dr. Komisaris. I'm going to provide the pre-lecture material by walking through a very reduced version of the handout. This is the lecture for PHA 3030, the Intro to Biostats. This is the lecture on scales of measurement. Bing! That means go to the next slide. So this is really the essence of today's discussion. There are really four scales of measurement, also called by in some texts the levels of measurement. There's a nominal, an ordinal, an interval, and a ratio scale, and we're going to talk about what that means, what are some of the features and properties, and what are some of the consequences of having data from different scales of measurements. So first let's talk about a nominal scale. Nominal scale is really a situation where it's based on identity properties, based upon the data are expressed as frequencies of occurrence. They are from what are often referred to as mutually exclusive categories. So what do I mean by that? Let's say you have a bowl of fruit. You got a bowl of mixed fruits. It is a nominal way to describe the data to say, well, there are 3 bananas and 2 oranges and 5 apples. You can't get any more than that, and we know that the apples are also not bananas. They're mutually exclusive. The inferential statistic that's used the most with nominal data is referred to as the chi-square. And we'll have a bit of a sidebar trying to explain what inferential statistics are. It's really not the topic of this course, but it's really the topic ultimately of biostatistics. Inferential statistics are the ones that are used to make comparisons between 2 sets of data. Usually you'll have a group of control and a group of treated, or it's even more complicated than that. But essentially use an inferential statistic to compare the data in one sample to the data in another sample to determine whether the treatment did something that was statistically significant in some way. Some common inferential statistical tests include t-test and ANOVA, which probably people have heard of, Mann-Whitney U-test, and chi-square. Hopefully you've heard all those different terms. The issue, or one issue with inferential statistics, is that they have differences in what's called relative power. That is the ability of a test to really pick out a difference. And it's really highly dependent upon the scale of measurement, the level of measurement. So what we're talking about today, levels and scales of measurement, feeds back to the relative power of a statistical comparison procedure. And power in the statistical world means the ability to significantly detect a difference when it's really, really there. With that as a digression, let's go back now. So nominal data was sort of categories. Ordinal data is really a comparison about magnitude properties. It's sort of a ranking thing, but the intervals are not necessarily equal. In a horse race, for example, they take first, second, and third win, place, and show. But you could be the first place horse by a nose, and you're still a first place horse, and you're still a second place horse, whether you lose by a nose or whether you lose by 25 lengths. It's not the time itself, it is the place, the relative position, the ranking, if you will. In the case of ordinal data, the median is used as a measure of central tendency, and we'll talk about what central tendency means next week. The inferential test is commonly something like a Mann-Whitney U-test. We'll talk about that a little bit later. But really it is the magnitude property. For an ordinal scale of measurement, everything's on the same line, if you will, on the same scale, but it's not a mathematically equatable scale. And the classic ordinal data that you all have to face is the issue of grades. In any given class, in this class, there probably will be scores on the statistics portion of the exam that range from probably the high 50s to probably the high 90s in terms of percent correct on my examination. But I'm not going to give nobody in the class is going to get a 72.3 or an 81.6. People will get A's, B's, C's, maybe D's, hopefully not. And that's converting it to an ordinal scale, because the reality is my B at 89% is no better than somebody else's B at 81%. But I know it is, but it's not, because in an ordinal scale of measurement, a B is worth 3.0 points. And so grading is an ordinal scale of measurement, because it's really not equal intervals. Not all A's are equally better than all B's. The Mann-Whitney U test is the test that's used as the comparison test, the inferential test, and again, it's magnitude property. I want to sort of reinforce this. If the data are ordinal in nature, the real difference is you really can't do four-function math. You can't add, subtract, multiply, and divide those numbers, because they're not on the same scale. My B at 89 is a whole lot better than someone else's B at 81, and there's no way that you should equate them and say they're the same, but on an ordinal scale of measurement they are in fact the same. So when universities, Wayne State and everybody else in the world, does GPA calculations using grades, they're violating a core statistical principle, because there's not equal interval between all letter grades. The mean shouldn't be calculated. It would be meaningless. It's really essentially useless. The median is really, when you have ordinal data, the median is the measure of central tendency for ordinal data. And we'll talk about central tendency next week. So that's an ordinal scale. An interval scale is a situation where you have ranks with equal intervals, which means it's suitable for four-function math. Central tendency measure is the mean. Statistics are all of our friends. Everybody's heard of a t-test. I hope probably everybody's heard of an analysis of variance, an ANOVA. A lot of calculations that we think of in terms of statistics, the standard deviation and the variance and the standard error of the mean, all of those are allowable when the data are from an interval scale of measurement. And the reason is that an interval scale of measurement comes from a situation where each of the intervals is equal. Not just this one's better than this one, this one's better than that one, this one's better than that one. If I can jump 3 feet and someone else can jump 4 feet and someone else can jump 5.5 feet, we're not just for second and third. There's an actual number of feet difference between us in terms of the jump, and that's meaningful, and that can be used in a lot of calculations. So an interval scale of measurement has equal intervals. It is suitable for four-function math. The central tendency measure is the mean. All of our commonly used friends statistical comparisons like t-tests and analysis of variance are allowable typically. Again, just to reinforce, these four-function math calculations, addition, subtraction, multiplication, and division, are not meaningful when the values are ranks. If the data comes from an ordinal scale, you can do it. I can calculate from your GPA, from your grades in the course, I can get an average GPA for this course. But it's meaningless, because I've started with ordinal data and I've treated it as interval data. Most statistical calculations require four-function math, so in order to do a lot of the fancy statistical stuff, you want to have at least interval data. And that's a huge hurdle, that's a huge important point in understanding scales of measurement. As I said before, the scales sort of restrict or limit the kind of inferential comparison that can be made. Inferential comparisons using interval data, things like t-tests and analysis of variance, are more powerful than things using ordinal data, Mann-Whitney U test for example, or nominal data, chi-square kind of test for example. So what's the last scale? The last scale is a ratio scale, and the difference between a ratio and an interval scale is that a ratio scale has a true and absolute 0 point. But the reality is that's of no consequence, of no major consequence in biostatistics. For all practical purposes, there's no difference in the utility or handling of data from a ratio versus an interval scale. If you want an example And ratio scale would be like temperature, which has an absolute 0. 0 degrees Kelvin. Four-function math is okay with a ratio scale. You can calculate mean, variance, standard deviation, etc. The t-tests and ANOVAs are the classic inferential kind of comparisons. But again, from a practical point of view, there's no consequence, no consequential difference. I guess that's a duplication of the same term. There is no difference between the utility of an interval scale of measurement versus ratio scale of measurement. There's a huge difference going from a nominal to an ordinal scale, from an ordinal to an interval scale. But from an interval to a ratio, there is no practical consequence. Again, ratio data is interval data with a true 0. There's really no difference in terms of handling data from ratio versus interval scales. So these are the scales of measurement. This is your glossary, if you will. Nominal scale really is simply how many occurrences are in this category, which is defined as by an identity property. How many males versus females? How many apples versus oranges? How many cars versus SUVs? Those kinds of things. Ordinal data is data along the same scale, but not necessarily with equal intervals in between. So it looks at magnitude, but it doesn't look at the measurement of that magnitude. So first, second, and third, biggest, middle, and smallest. But the intervals are not necessarily equal, and that restricts what you can do mathematically with those numbers. Interval scale of measurement has equal intervals, which allows for all the classic four-function math that's necessary to calculate an average, a mean, a standard deviation, those kinds of things. Ratio scale is an interval scale simply with a true 0 point. Again, for all practical points of view, from a statistical perspective, there's really no consequential effect of an interval versus a ratio scale. They are both very useful in terms of in comparison to ordinal versus nominal scale of measurement. So let's try to summarize. I think you need to know the 4 levels or scales of measurement to be able to identify them. Nominal, ordinal, interval, and ratio. Know what you can and cannot do with them. Four-function math is important for a lot of the powerful statistics. Know that interval and ratio scale, there's not a difference there, but the main issue is that with the interval and ratio scale you can do the four-function math, and so you can do things like mean and standard deviation and all those things. We'll talk about those later though. Lower scales of measurement have less statistical power. That is the ability to find or show a significant difference when it exists, and therefore people really try to avoid them if they possibly can. And what I mean by lower scales is nominal is the lowest. The categories analyzed with a chi-square. Ordinal is the next lowest. That's a ranking, typically a Mann-Whitney test, and median is the way to describe the central tendency, if you will. Interval and ratio are the most powerful and are really comparable in terms of biostats. And they have the most statistical power. And again, this is today's discussion. We'll talk about this a little bit more in class, and we'll start out with a quiz at the beginning of class. Thank you very much for your time.